Okay, let me get ready. Are we on? You all set? Okay, this is the fifth in a series of lectures on semiconductor components, their operation, and their characteristics. And it is given for a class of diverse jobs in the semiconductor field, so we'll keep it in a general manner. Today's lecture is on silicon-controlled rectifiers, and my name is Jack LaFleur. Okay, and talking to Dave Bushmeyer, after he came to the first lecture and talked to me, and he said, since SCRs are different than other things we're using, I'd like you first to start out with giving a description of how they're used and work into your component in that manner. And so I've done that, and I'll tell you a little. A silicon-controlled rectifier is a 3-junction, 4-layer device that works similar to a transistor. And what it is, effectively, is an off-on switch. No different than this ordinary switch, a mechanical switch that you might use in a light fixture. It has 2 states. When the switch is open, it blocks the applied voltage. When the switch is closed, it provides a very low resistance path to the flow of current. And so we use it in the circuits in that manner. Now, I have 2 circuits on the board, and the first one I'll explain, and because it has an analogy to something you're all familiar with, and that's a light dimmer, the kind where you have over the dining room table and you turn down, and it makes a very effective light for dining. Now, all light dimmer circuits are not these. There are several designs, and this is a very simple thing I put together to explain it. And what happens is this. An SCR can be controlled so that we can control the phase of the AC current going through, the amount of AC current going through the light. So if for example, we turn on a light, you got 120 volts, and you get the full brilliance of the light. Now, if you want to dim it, what you do is you have to reduce the current going through the light, the overall current. And the way that's done with an SCR is quite simple. We have an AC signal coming right off the power line going in to light your lights. Now, the lamps over your table are the load. The SCR is connected across the AC power line, and we have the gate. The gate controls the SCR, turning it on. Does not turn it off, it turns it on. And so what I've shown here now is the positive half cycle of the AC signal, and the part that is plain is the part where the current does not flow through the lamps. As it hits a certain, by the way, we can use, it controls the phase so that we can turn it on any point as this voltage goes from 0 to 120 volts. By varying the current going into the gate, we can turn it on at any place along the way. We have an AC signal coming in. Now, the reason I put the diode there is so it'll block in the reverse direction and we're not bringing current back in the opposite direction. Now, if I want a very dim light, I turn it on about halfway up. The SCR conducts. The current goes through the lamp. As it goes through the negative cycle, the SCR turns off because we no longer have a positive signal on the anode. The lamps do not get any current in the half cycle, and on the positive half cycle again we do the same thing. The SCR recovers. At a point it turns on, current flows through the load, and the lamp is a very dim light. And you can adjust it with a variable resistor. Now, if you want the bottom half to conduct current, I've just made a little diode there which bypasses the SCR. We can use that with a plain switch, and with this switch closed, when this half cycle goes positive, we got current flow through the lamp, so we have a brightness, and that we can turn this SCR down so that it turns on almost at 0 and you get full current through the lamp, or you can turn it off until it goes to the peak and you get only partial current through the lamp, so you get a light dimming circuit. That's one use of an SCR. Now at Sandia, we use SCRs in a different manner. Mostly we use them in what we term capacitor discharge circuits. And they do certain things. They provide a switch to turn the current on when we need it. And I have a circuit here to show you how we use it primarily at Sandia. But here's the way a capacitor discharge circuit works. Let's assume now that we have a weapon, a bomb, hanging on under a 111, and the pilot comes in on his target and he decides to fire the weapon, and he hits the bomb release. Now when the bomb drops from the aircraft, we have a cord on there, and as long as the bomb is attached to the airplane, it uses the power supply of the aircraft to provide the power that it needs inside the weapon. As the explosive volts blow off and the bomb falls away, then a cord is pulled out, which is the power cord to the airplane, and that triggers all the mechanisms for power inside the weapon. And then they go on internal power, and we have batteries in the weapons that provide load. So what I've shown here is a DC power supply, which is, in all probability, inside the weapon is a battery. And what we want to do now, when this bomb falls away, is we want to open the tail fins so it has some guidance. An explosive squib has a bridge wire that is about like the wire inside a light bulb. And when current goes through it, it heats up, and it fires an explosive charge. And the explosive charge now usually drives a piston, because the gas from the exploding charge exerts a great deal of pressure, and it drives a piston. And this piston, in this case, we fire the explosive charge, and the piston opens the tail fins, and the weapon falls away. Now other things happen inside the weapon, and we do use SCRs at other places, but this is a little hypothetical case. Now here's the way this works. When the control signal tells the DC power supply to come up to 40 volts, it does so very quickly. And what we have here is an RC network, a charging circuit, in which the voltage now is 40 volts, and that capacitor starts to charge. And it charges at the rate of whatever the RC time constant is. And you notice I have a 24 volts over here on the zener. Now, it is charging up toward 40 volts. The reason we pick 24 volts is because that's the linear portion of the charge curve. And much of the firing of SCRs in the weapons is based on how much time it takes. The time is very exactly fixed. And so usually we try to fix it so that it's in the first RC time constant, the linear portion of the charge rate going up. Now what happens is this. As this charges toward 40 volts, the capacitor begins to get a charge on it. When it reaches 24 volts, this zener now, which has held off the voltage, this zener starts to conduct current. The current turns on the SCR, and when the SCR turns on, this capacitor discharges through the SCR. It's a switch. It was off. When the gate turns it on, it becomes a very low path. The current goes through, lights up the bridge wire, fires the squib, and the fins open on the weapon. And it happens very quickly. It's a very closely timed circuit. Now, later on, I'll tell you why we used 7,500 ohms in here, and we'll get into some of the other operations. What I'm trying to explain with the two circuits I show you here is the fact that an SCR is a device, a switch that has two stable states. An off state in which it blocks, and an on state in which it has a very low path of conductance, the on state. And remember, we're not going to talk about circuits today. We're going to talk about the SCR. So I'll take this off the board now, and we'll start explaining how an SCR does this thing, blocks and conducts. And that's really the main topic of the conversation. Many years ago, before semiconductors, we used tubes to do approximately the same thing. They were called radio tubes, and then when we got into electronic circuits, they were called electron tubes, and they worked pretty good. And we had a device at the time called a hydrogen thyratron. It was a tube. We used them here at Sandy. I was probably the last fellow that ever had anything to do with a tube around here, except the special tubes that we use today, like the Crytrons. But the hydrogen thyratron was a very effective tube for the same purpose that an SCR is used for, an off-on switch. And here's the way it worked. First of all, we had something we called the cathode. Now, the cathode was a piece of wire like a wire in an incandescent lamp. And it had coated on this wire, it had some kind of earth metal, which was very rich in carriers, in electrons. And when you heated the wire, put a current through it, with a battery, or however else you wanted to do it, the wire got hot, and these electrons, and I'm using the word electrons, boiled off around this cathode. Now we had up here, some distance away, and the spacing was critical, we had something called a plate. And when you put a positive voltage on the plate, and a negative voltage or the ground on the cathode, the positive charge attracted these electrons and they went to the plate. Now, we had something called a grid or a gate, which was a wire mesh like a screen on the window to keep the bugs out. Only it was tighter, but just like that. And that was located closer to the cathode than to the plate. But it came out and it was called a gate, and this was called an anode. Now, if you put a negative charge on this gate, and the electrons were bubbling around here, it cut off the path of the electrons between the cathode and the plate because the negative charge repelled the electrons and they stayed in this general area. So that you could apply a voltage to the anode and it would hold this voltage off. Now, since this was a hydrogen thyratron, we put a glass envelope around it and we put a gas inside of it. And we put hydrogen, however you spell it. Now, hydrogen gas served the purpose later on of providing a very low conducting path. Now, this hydrogen gas, the pressure inside the envelope was critical and was determined by how much voltage you wanted to hold off. In other words, if you wanted to hold off 100 volts, you would have a certain pressure. If you only needed to hold off 50 volts, anode to cathode, you would put more gas inside because that provided more carriers. Now, if you wanted to turn this device on, you notice the neon lights we have up here. They have a different gas in, but the principle is exactly the same, and that's why I wanted to explain this. When we wanted to turn this on and go from the off state to the on state, the same as we do with the SCR, you put a positive charge on the gate. You came in here and you put a positive voltage on the gate, a pulse. And what that did then, now it turns the gate positive. Where it was rejecting the electrons before, it now is going to attract them. And these electrons shoot through the screen. Rather, we had, as I said, it was like a screen on the window. They head for the grid, and they pass through the grid, and they are attracted to the plate. Now, in the process of being attracted to the plate with a high voltage, they have a high velocity. They smash into the hydrogen atoms, and they knock off the valence electrons in the hydrogen atom, and they cause ions, where we have both positive and negative charges. Now, what the gas does when it's ionized, just like the gas glows here, it provides a very low path of conduction. So in the old hydrogen thyratron, we had a conductive path, a low resistance path made up of electrons and ions. Now once the tube ionized and went into conduction, the gate had absolutely no control over the device. The only way you could shut that device off was to put a negative voltage on the gate or remove it, or I suppose you just break the circuit. Now, the reason the gate had no control is because if you put a positive charge on the gate, negative ions would collect on it and neutralize the charge. If you put a negative charge on the gate in hopes of repelling the electrons, negative ions or positive ions would collect on the gate and neutralize the charge. So the gate never had any control. Now, why do I tell you about an old tube called a hydrogen thyratron? It's because when the semiconductors were first being developed in around 1955, that period of time, General Electric, who was a big manufacturer of tubes and hydrogen thyratrons, decided they could make a semiconductor, a solid-state device that would do exactly the same thing. And we had two physicists by the name of Evers and Moll who did most of the modeling and characterization of solid-state four-layer devices. And General Electric made the first semiconductor silicon-controlled rectifiers. Now, the reason I wanted to show you that is because we go from the hydrogen thyratron and the thinking that was in the development of that to the solid-state device, which is the SCR. Now, and when they transferred the technology over, they used much of the same terminology that we used in the old hydrogen thyratron. And a three-junction four-layer device, we have PN, PN. They called the anode, it was the plate before, they call it the anode, just like we did in the old hydrogen thyratron. They called something we call the base in the transistor, they called it the gate, which was the control grid or the gate of the old hydrogen thyratron. And they called the negative terminal the cathode, the same as we talked about in the cathode of the device before. So some of the terminology carried over because same people developed the tubes, worked on the solid-state device. And in, I guess General Electric in about 1955, 56, 57 brought out the first silicon-controlled rectifiers. Now, let me say this about that. The term they used then was thyratrons. No, I'm sorry. Thyristor. Now, we had a hydrogen thyratron before us. They called this device a thyristor from the old hydrogen thyratron and the transistor. Now, the SCR is only one, although it's the predominant one, of a family of four-layer devices that come under the heading of thyristors. So you'll see that term around, thyristor, and it is in reference to a family of four-layer devices that we have here. We have some without a gate. We have some with two gates. And there are various other configurations. We have something now called a triact, a triode AC, which works directly on AC and will conduct in either direction. They're all part of that same thyristor family. Now let me find out where I am, and we'll go from there. Okay, now we're into the discussion of how an SCR works. I'm going to put this same picture that we had here, I'm going to put it horizontal because I think it's easier to talk about that way. Okay, you'll know something here. In a 4-layer device, what we really have is two transistors. We have an NPN transistor and we have a PNP transistor. And we can explain the operation of an SCR by explaining how the two transistors within the structure work. So I'll redraw this a little bit and we'll do it this way. We have the P anode, okay, we actually have a PNP transistor and an NPN transistor. Now they are connected in what we call the common base mode. Now we have common base, common collector, common emitter. And in explaining this, we will see how the two transistors react to provide feedback to keep the device in a when it's on, in a very low resistance state. Now, let me see how I'm better draw what we have with transistor symbols. Okay, I'll label these in a minute, but I want to show you something. If I take a transistor and we use a NPN, remember a transistor can serve as a switch too. You can turn on a transistor till it goes in saturation and has a very low forward drop. Or you can turn it off with the gate, with the base, and it conducts no current and it has a very high resistance. So it has an on and off position if you want to put it on full saturation or you want to turn it off. And that's the way a transistor is used in digital integrated circuits. It's off or it's on. In most cases, the outputs, things like that. Now, if I were to put a signal in here, a positive pulse in this NPN transistor, and look at the output, as Al says, he always likes to have a resistor in there, but if I were to look at the output, what would I see? Okay, I am turning this transistor on as hard as I can turn it on. I'm putting it in saturation. So the voltage goes from whatever the anode, or the collector voltage was there, and let's say it was at 30 volts. I am going from 30 volts here, because when there's nothing conducted, and I go across here with a voltmeter, I'm looking at 30 volts. It goes from 30 volts to when I turn the transistor on, it will drop to the side of the transistor, and as long as the period, the time I keep that gate on, that transistor will stay on in sat, and when I take this signal off, when it drops down to 0, it'll go back up to 30 volts. That's the way a transistor works. Now, so I can do that. That's the same transistor, and I can do that to the SCR. Okay, now, with an SCR, we have one transistor, a PNP, feeding an NPN transistor, and it works just a little different. And I'll label these so we can see better the explanation. That's the current in the anode that we're talking about here. This is the base current, and I'll call it IV1 for the base. We'll call this transistor Q1, this transistor Q2. This is IC2. It is the collector current for transistor 2. This is the base for transistor 2, and the cathode current. Let's see if I left anything out. Okay, now what I want to show you in this two-transistor explanation is that the transistor, the PNP, turns on, and the collector current in the PNP transistor is actually driving the base of the second transistor, the NPN transistor. Now, when we put a gate signal in here, it turns this transistor on. And the first thing that happens is it conducts current. And when it conducts current, it is pulling current out of the base of the PNP transistor, so it is turning that transistor on. Now, we have, in this case, the PNP transistor collector turning on the NPN transistor, and we have the collector current from transistor 2 pulling current out of the base of 1. So we have a regenerative feedback mechanism. So when I hit it with a short pulse, this goes into conduction. We have more current flowing, and the more current flow through the anode and the cathode, the tighter these two devices turn on, and we have a feedback mechanism that locks these things in a full conduction state. Both transistors are in SAT, and we have a very low conduction path between the anode and the cathode. Now, remember I said in the transistor I showed you here, we can turn the transistor on, but when we turn it off, it shuts off. When we turn the SCR on with this regenerative feedback, what happens, of course, is it turns on very strongly and stays on. Now, the gate no longer has any control. Just as in the hydrogen therotron tube, the gate no longer can control the operation, and the device stays on. So when you use an SCR, with selected cases, when you use an SCR, once you turn the gate on, the gate loses all control, and you cannot turn it off with the gate. The gate has no function whatsoever after the device turns on. Now, how you turn them off, we'll talk about later. I want to show you something else while we're right here, and I'll pick a place to put it. Okay, we have a transistor, a PNP, and we have the collector current. Over here we have the emitter current, IE. Here we have the base current. Now, I want to show you just a couple things in the way of equations, so that I can show you how the alphas work. Remember I said we had a common base connection when we had when we used the transistors in the SCR. They are connected in the common base configuration. We have three configurations: common base, common emitter, common collector. This is common base. Now, in a common base connection, we talk about the alphas of the device. This is a convention. The alpha of a transistor is equal to the base current over the emitter current. Now, it is called the common base current gain. So when we look at this transistor, and then it's the same as we have here, what we see is the base current coming out of here IB1 is the same as IC2 that we said here. So it's the same current. IC2 and IB1 are the same currents. Now, they are equal to the alpha of the cathode current, IE, or IK, plus ICBO, which is leakage current, and for the moment we won't get into that. Now, why I wanted to tell you that is when these devices turn on, or when these devices are in the blocking state, when the SCR is blocking and these transistors are not on, we have extremely low alphas, and it will block the device because the gate currents or any feedback here is almost all leakage current, and the alphas are so low that they do not turn on. When we hit the gate with a signal and we start conduction, the harder the emitter currents turn on, the higher the alphas go. And what we're saying is, if alpha 1 plus alpha 2 comes close to 1, then we have, if the feedback of this device, if the current in transistor Q1 is strong enough to keep on this Q2 in SAT, and the base current, the collector current IC2 is strong enough to keep the base of Q1 on and keep this transistor in SAT, as long as the alphas are close to unity, that device will turn on and be a very low current path. Okay. So what, in summary, what we're saying is we can go from the blocking state to the conduction state with a very, very low value of gate current. When I turn on this transistor and put it in SAT, if I'm conducting, let's say, as a figure, let's say 2 mils, or 2 amps, I probably have to have a signal to keep that in SAT of somewhere around 200 mils. In an SCR, I have to have a very short pulse of maybe 5 to 10 mils, depending on how sensitive the SCR is. So I can use, if I had to build a circuit to supply 200 mils to keep that on for a short period of time, I'd have to have a fairly large circuit to supply that current, and when I took it off, it would stop. On an SCR, I need only a spike. So a very low control current can influence a very high load current. I can turn it on with a very easy pulse. Okay, so much for the turn on now. We understand how an SCR turns on and stays on. Let's see how it does the blocking, and I'll get rid of this stuff on the board. See where I am here. Okay, we'll go back to the same figure we had before. Anode, cathode, okay, we have 3 junctions. In describing now how the device holds off the applied voltage, I want to talk a minute about the doping profile of an SCR. First of all, let's talk a little about what we have to refresh your memory about what we're talking about doping. We have a bar of very pure silicon, very pure. Okay, the silicon has the lattice work of the atoms of the silicon in the structure. Now, we call it a semiconductor because it is not made of porcelain or glass. It is not an insulator. It can conduct current. It is not a bar of copper, for example, that literally floods with carriers and conducts current very readily. It is something between a conductor and an insulator. It is a semiconductor. And now to provide some control on how that conducts and how we use it, we dope this silicon with impurities to provide carriers. Just as we provided in the thyrotron, we had the gas, or the neon gas and the light, to provide carriers, and we had the electrons coming off the cathode. We need to provide some kind of carriers inside the silicon, so we dope the silicon. Now, the more impurities you put in, whether they are donor atoms or acceptor atoms, the higher the doping level. And to give you an idea where we are, what we're talking about, in this P layer, which is we call the anode, in the P layer, we will dope in for an SCR in the neighborhood of somewhere around 10 to the 19, 10 to the 20 impurities per cubic centimeter. Now, what does that mean? That means we have in the atomic structure, we're putting Allen's old oranges there, with atoms of, in the case of P device, boron atoms, and we're putting them in there. They're not uniformly put into the silicon. I should say they're not put in a uniform manner. The concentrations can be heavier in certain areas and lighter in other areas, but by and large, if you were to count the number of impurity atoms in it, it would be 10 to the 19th, 10 to the 20th per cubic centimeter. Now, that is a fairly high doping level for an SCR. So that's a fairly highly doped P region. Now, when we come to the N region, I think they use phosphorus, and they dope these with carriers and phosphorus atoms, and it is a similar doping as we did to the P region. And in this junction area, you notice I always draw it larger than the others. We put the doping levels fairly low. It would be N, and it would be a donor, and it would be like 10 to the 14th, 10 to the 15th. Much lower than we have the other. So the doping level here is fairly low. When we come to the P junctions, it is close to this. And we come to the N emitter, we want them pretty rich for emitter. So usually in the N area of the cathode, we'll dope it at about 10 to the 20th, 10 to the 21, in that level. Okay. So you get an idea now of what we have in the doping profile of an SCR. The anode, P anode, is fairly heavily doped. Something we call the anode base, the N area here, is very lightly doped. The gate is fairly heavily doped, about the same as the anode. The cathode is quite heavily doped, more than anything else, because we're going to use the cathode as the emitter. And they're going to emit the carriers, or emit the carriers. Okay, now let's talk about blocking. We have 3 junctions, and I'll show you the biasing in a minute, but let's talk just for a second on a diode. About the biasing. Now, if this is a P area, and this is an N area, same as we have here, and we have the junctions, same as we have there. If I reverse bias the junction, put minus here and plus here, what happens? We get a depletion area in here, and let's just say that I put 30 volts here and ground this. Now, if I go across that device, there's no current flowing, and I'll show you why. But I measure from anode to cathode, I'll measure 30 volts on the voltmeter. Now, what happens is this. The carriers the free electrons in the holes, the free ones, move back because I've got a plus on here. So the donor atoms, the electrons, move back from the field and collect here. This junction is not as highly doped, more highly doped than the N junction. And we have holes here which are attracted by the negative. The acceptor atoms will move back and give you a field here. And this field is 30 volts. Now, what has moved? And this is important. The atoms have not moved. The silicon atoms and the silicon lattice work are intact. Every atom is intact. The carriers or the electrons are still spinning around. The impurity atoms are still intact. Nothing has moved but the loose valence electrons and holes, the carriers, have moved back from here. The atoms themselves are still in place. The silicon atoms, the impurity atoms. So that has not changed. All we have done is pull back the carriers. Now, since there are no carriers in here, I can sustain that 30 volts because the junctions have been doped to withstand 30 volts. Now, what happens when I raise that? Let's say I go to 40 volts. Okay, when I go to that much, now the doping profile is such that it's going to sustain, it's made to sustain about 30 volts. Now, as I go up to 40 volts, this field expands. And it'll expand to 40 volts. That pulls back. But we have given a lot more energy now to the carriers, and they start tearing loose. And the minority carriers, which are holes that are over here, and electrons that are here, the minority carriers that are always in there somewhere, start, motivated by the very high voltage, start flying up to the junction, and they start knocking off, running into the lattice work and knocking off the valence electrons that are in the structure. And now we're creating whole electron pairs, or we are creating more carriers. So the reverse voltage now has given enough velocity to the carriers and has started to pull off and move the carriers very rapidly toward the junctions. And the current now will start to increase. So the current goes up. When the current starts to go up, the junction starts to break down. When the junction breaks down, it goes into what we call avalanche breakdown. More and more carriers are running into the lattice work, into each other, and they're creating more and more whole electron pairs or carriers. And so this junction can no longer sustain the reverse voltage, and it breaks down and conducts in the reverse direction because we haven't changed the polarity of the voltage. That's how a junction is able to sustain the applied voltage in the reverse direction to hold off. And that's how, when you increase the voltage too high and you get the breaking up of the creating of whole electron pairs, the junction breaks down and you get reverse breakdown voltage. Now, the way we hold off voltage in an SCR is just the same. We put a positive voltage here. And let's look what happens to the junctions. We put 30 volts here on the SCR. You want to keep that switch open. You don't want it to conduct while that's charging up toward 24 volts. In this case, I showed 30, but it's charging up now, and you want that to stay off, be a very high resistance. In the first place, now you have a PN junction that's forward biased. So that's not going to do any good to hold off any voltage. But here you have a reverse bias junction. You have the N area and the P area of junction 2. That is reverse bias, and that is the junction that sustains the hold-off capability of the SCR. You'll get, because it's lightly doped, we'll get a depletion region in here that will sustain the 30 volts. Now, if I were to raise up this thing above its ability to sustain the applied voltage, it would break down, the same as the junction we talked about here, and we go into avalanche breakdown. This junction is also forward biased, so it is no help. The blocking junction on an SCR is the center junction. And the doping level in the N area pretty much determines how much voltage it will hold off. And we have SCRs going from 30, 35 volts without special effects up to around 900 volts. And we have some at Sandia that will do that well. However, most of our devices we use are under 100 volts. Okay, let me see where I am again. Okay, a quick explanation now as to what happens, again, with holes and electron pairs when we turn on a junction. Let me get this straightened out just a minute, and away we'll go. Okay, now talking about turn on, this is the gate. Again, in an SCR that's blocking, and we'll talk about quickly in terms of carriers. Mother Nature likes everything to be at an equilibrium. So she has the junctions that stand off there and there's no activity. We applied 30 volts, and the 30 volts, this blocking junction has sustained the 30 volts, and we got a forward bias junction here, and everything is calm. And you're holding off your voltage. Now you come along and you hit it with a gate signal. And what that does now is we are putting carriers into the gate region. This is the P region. Okay, now we have unbalanced that junction. And we have more donor atoms or over in the P region than we have on the, over here in the N region. So what happens immediately? The emitter starts to emit carriers, electrons, and they go across the junction and are collected here at junction J2. They are collected here. You've got N-type carriers that pass through the P region and are collected here. Some of them recombine, we lose some of them, but this unbalanced junction now gives them enough mobility to go over and are collected here at junction J2. Now what does that do? Now we have these electrons that came across here, and they are now in the N region where they are minority carriers. Now we have more carriers in the N region than we have here in the P region. We have unbalanced this junction. So what does this do? It starts to bring things back in balance, so it starts to emit holes. And the holes go across this N region where they are minority carriers, and they are collected at this junction. Now, what has that done? It has, we have now changed the equilibrium of the blocking junction. We have put carriers in from the N region, we have put holes in from the P region, and this junction now cannot sustain 30 volts, so it drops down some. The P region holes that were collected here are now majority carriers in the P region here. That junction is again unbalanced, and the emitter throws more and more electrons, which do the same thing. So we have electrons flowing through the region and are collected here. We have holes that have gone through the region and are collected here. This junction cannot sustain the 30 volt hold off that it tried to do. The junction breaks down and we go into conduction. Now the SCR is a very low conduction path because this field has collapsed. Now what does they look like when it goes in conduction? Okay, this junction is forward biased. We have PN, PN. If the junction is forward biased, we have plus to minus. This junction is forward biased, so we have N plus, N here and plus here, and this junction is forward biased. Because the condition of saturation is that the junctions are all forward biased. When we put a transistor into saturation, we forward bias the junctions, and that's what we're doing here. And if you should take a gate lead out of here and a gate lead out of here, and you should look at the voltages. You would find you get plus to minus here, minus to plus here, and plus to minus here. We can measure those junctions. That's how, with the carriers, the holes and the electrons, that is the current flow that causes the turn on in the SCR. Okay, very quickly, I didn't realize it, but we have run out of time, so very quickly I'm going to sum it up and see where we are. There are a lot of things about the SCR that we can't talk about because of time. Now, I had a curve tracer set up here, and I was going to show you how to test an SCR, but we don't have time to do that. But quickly I can show you on a current voltage curve what happens. We have voltage in this direction. This is current in this direction. In the forward blocking condition now, I have very little current flowing as I push higher and higher on the anode voltage, and I get out here to a point, and we use 30 volts as an example, where we're passing now the breakdown voltage. So when I can no longer apply the anode voltage and have it extend, I'm going now, it starts conducting current because we're getting into avalanche. And I crank more and more voltage into that. I go to 35 volts, but 35 volts don't come out. It still pegs here at 30 volts. The junction breaks down, and when it does, it swings back here in what we call the negative breakdown region, but it'll swing all the way back to a point where we have almost no voltage. It's a very low on state where we have almost no voltage, and that point right there is called the holding current. And what that is the minimum current where the alphas will keep both those transistors in conduction. Then as I crank more voltage, I will get a raise in the current. Now if I were to go in the reverse direction, I will go out in the reverse direction on the SCR, that is where the cathode is positive, the anode is negative, and I will go out to a place where we'll get avalanche breakdown again, but it will not go back negative because the junctions are biased wrong and they cannot sustain this feedback we talked about in the reverse direction. So your SCR will not conduct in the reverse direction with very low impedance. You will get current, but it'll be high impedance. The reason for that, very quickly, and we'll write this up, is that the junctions that are sustaining it in the reverse direction are the J1, J2, which are reverse biased. This junction is forward biased, J2 is forward biased, and we do not have a feedback mechanism where we can keep the device, the SCR, on in the reverse direction as we do here. Let me see if there's anything else. Okay, quickly, triggering methods, we use the gate, as we talked about. We can use, we can increase the anode voltage until it triggers on. That does not hurt the device, by the way. It may hurt some of the other devices. Now, when an SCR goes on, the only thing that controls the amount of current flowing is the resistance in the external circuit, the load. So you always must have a load on an SCR when you turn it on, or else the high currents will burn it up. So it's you have to calculate your load to make sure that the current going through the SCR is within its rated capability when you use it. Another thing that will turn it on is light. If I shine light, this SCR I have here has a glass top. I'll just pass it around to show it to you quickly. That glass top, we used to turn that on with light. We used that in a missile, and they wanted to test the missile out over the Pacific. They shined a light in that device, and it turned it on and did whatever it had to do in recording data. Now, the important part is that the turn-on characteristic is essentially the number of carriers that pass the junction area. So that if you shine a light on there like a flashlight and it isn't very bright, it conducts It has very few carriers moving through. The SCR will not turn on. If you hit it with a xenon flash, the very bright light produces a lot of activity and it will turn on. I don't have time to talk about the turn-on mechanisms we have. I'll just end it by saying, do we have any questions at all about what happens on the SCR? In using them, remember that heat affects turn-on. That is temperature. The radiation affects turn-on. In a gamma radiation, they will turn on. So if you have voltages across the device and it's hit by gamma radiation, it will turn on. It will trigger it on. So in using the devices, you have to be careful to use them within the manufacturer's specifications. That's all I had to say about that. Thank you. Now I'm going to give you the